Alright, in this lecture we want to discuss rectangular waveguides. I'm already seeing a spelling error. I guess I was tired when I made this out. But we want to discuss rectangular waveguides, so we'll skip over my error and we'll go right to illustration of the metal rectangular waveguide. The difference here between this and the parallel plate waveguide, as you can see, in addition to a dimension in the Y dimension that has walls at 0 and B, we now are going to place walls in the X dimension as well. So we don't have open edges and we can't assume an infinite direction or an infinite width of the waveguide. So the textbook author has flipped coordinates a little bit, and now we have we're going to have a boundary condition at 0 and B in the Y direction, and at 0 and A in the X direction. Before we did have 0 and A in the X direction, and Y was unbounded. So it looks like it's flipped. It really hasn't. It's just changed in how it's illustrated. Now, what this means from a practical point of view is that you're no longer going to have a constant distribution of the electromagnetic field in one direction, because now you're constrained because you have conductors on all four sides. So you're constrained to drive that tangential electric field to 0 at the walls by physics. So this is going to mean that we're going to have now not just a set of boundary conditions in X, but we're also going to have a set of boundary conditions in Y. So looking at what those boundary conditions are, the X and Z components of the electric field, because those will be tangential on the Y, in the Y plane, or in the walls at Y, those electric fields are going to have to go to 0 at Y equals 0 and Y equal B. So let's go back to the figure. So here and here, you can see that the X vector and the Z vector would both be tangential to the walls in the Y at Y equals 0 and Y equal B. So that tangential field will have to go to 0. And also notice that the tangential field will have to go to 0 at this wall and this wall, but the tangential field here will be the Z component of the electric field and the Y component of the electric field. So that's basically what this states mathematically. EY and EZ, and by the way, HX will have to go to 0 at X equals 0 and A. EY, EZ, and HY will have to go to 0 at Y equals 0 and B. And so what we're modeling here initially is we're going to model the transverse magnetic wave. So we will have no Z component to H. Once again, we assume the waveguides are perfect conductors and that all the fields will vary in the Z direction as e to the minus gamma Z, where gamma is either going to equal alpha or J beta, and you notice that it has a line over it. So that means this is the propagation constant within the waveguide. If gamma is real, once again we will have an evanescent wave because we'll have e to the minus alpha Z, where alpha is a real number. If gamma is J beta, then we'll have e to the minus J beta Z, and we'll have propagation within the guide. So the goal here is to figure out, by applying Maxwell's equations and the boundary condition and the wave equation, kind of all three simultaneously, the goal is to figure out what waves will and will not propagate in the waveguide and what are the parameters of those propagating waves in the waveguide. So now we realize that in Maxwell's equations, every time we take a partial with respect to Z, we will generate a minus gamma, and the Z variation remains the same throughout every term. So basically it will come out as a common term, meaning our Maxwell's equations for E and H will take the following form, where the partials with respect to Z have been replaced with a minus gamma. So the curl of H and the curl of E are shown here. And the wave equations for EZ and EH, just like in the parallel plate waveguide, can be found from the wave equation when we take the second partial with respect to Z, that's going to generate a gamma squared because it'll generate negative gamma twice. And then on the right hand side of the wave equation, you recall we had this term because it was a time derivative. So when we take that second derivative with respect to time, we generate this minus omega squared. The e to the minus j omega t is taken out of the equation so that we can basically have the time variation shown here in the differential equation, and we replace it later when we want time variation, just like we did with the parallel plate waveguide. And then we generate essentially the same equation for h. So these are just Maxwell's equations repeated again. And here we have made the substitution when you collect like terms over on the right hand side, then you can express h squared as gamma squared plus omega squared mu epsilon, introducing a new term. So we could rewrite these two equations with the h, and then we could go back to Maxwell's equations and make the appropriate substitutions. So for transverse magnetic waves, we assume that E varies in the z direction and H does not. So H won't have any zero variation. And it also will not have, H will not have a component in the z direction. Everybody varies as e to the minus gamma z, but H will not have a z vector component. E will have a z vector component, and so we could write that vector component as a function of x and y, e to the minus gamma z. So this is different from the parallel plate waveguide in that we're not constant in the, I believe it was the y direction, where we assumed we were constant and had infinite width. Here we're not. We're going to have both an x and a y variation. So once again, saying h is 0 in the z direction, I don't mean the variation of h, I mean h does not have a z component. Okay, so if we note here e is a function of x and y, what that means is when we now take our assumed solution for e and we plug it into the wave equation, we generate the following equation. And the difference here in the parallel plate waveguide is that we now have a differential equation of two spatial variables. So it has to remain a partial differential equation because we have variation in both x and y. So if you didn't have partial differential equations as a class yet, it's basically pretty straightforward what you do here. You're just going to make an assumption and allow some things to cancel out. So we'll just show the mathematical trick, and then once we've shown it once, I think it'll be pretty straightforward what it is. So what you do, the partial differential equation solution technique, is you assume the function can be written as the product of two separate functions, one that's a function of x only and one that's a function of y only, and this is a pretty good assumption. So now we take the wave equation, which was an equation in E, and we substitute this f times g into the wave equation. And when we do, and the part of the wave equation that takes second partial with respect to x is not going to operate on g, so it's treated like a constant. And the same is true for the part of the wave equation that operates on y. F is treated as a constant. So they basically come out of the derivative, and then we have the remainder of the expression. So you can do a substitution for h, and then you can do a little mathematical rearranging and put all of the variables in f on one side of the, or all of the terms in f on one side of the equation, all the terms in g on the other side of the equation. And because this equation has to be true for all values, then basically the left-hand side and the right-hand side will both have to be equal to a constant, and it'll have to be the same constant. So here's what we have. The left-hand side must always be true. The right-hand side must always be true, independent of what x and y are. And the only way that can happen is if it's equal to some constant. So we'll set both sides of the equation equal to a squared, which means we get two separate equations. So this is known as separation of variables technique, and it's a common technique in the solution of partial differential equations. Fortunately for us, in the wave equation, it's pretty easy. So what we find is that we get a solution for f in terms of sine and cosine, and we get a solution for g in terms of sine and cosine. And we can basically, in the f equation, we can move the h squared over to the right-hand side, generating another constant b, which is the square root of h squared minus a squared. So we have these cosine and sine functions in terms of a and b. So now to go back and actually create a general solution for e sub z, we have to take the product of those two. And so then we end up with this four-term expression with four different constants and four different products of sine and cosine. So this is our general solution. So at this point we need to apply the boundary conditions. So that will be what we'll do next. So remember that when we apply the boundary conditions, that field has to go to 0 at, let's go back and pull up the figure because I don't remember. I think y is b and x is a. Yeah, it has to go to 0 at y equals 0 and y equal b, and at x equals 0 and x equal a. So we have two parameters, height and width. So like we did in the parallel plate waveguide, we're going to apply that to this expression, realizing when we plug in 0 for b, all except for the first term will die away. When we plug in 0 for a, everybody except for the first term will die away. So we'll be able to get a boundary condition there. And then also note that when we plug in little a for x, we'll also generate some conditions on a and b. So when you do that, you come up then with, you have a constant that will be related to the field intensity or the wave magnitude. Then in the x direction, you have these modes m pi over a, and in the y direction, you have n pi over b, where m and n are integers. And then in the z direction, obviously, you have your e to the minus j beta z, assuming that you have propagation. So in this first set of equations, we're assuming we have propagation, and so we have the e to the minus j beta form. If we don't have propagation and gamma turns out to be real, then the equations look the same, except we have e to the minus alpha z, and this is an attenuating term, hence creating these evanescent waves. So we can go from phasor form to time domain form by taking the real part, and what you find is that for the imaginary beta, we get this cosine of omega t minus beta z, and for the real alpha, that remains in the exponent, and we just generate a cosine of omega t. So basically in the z direction for this evanescent wave, you don't have a traveling wave, you have a cosine distribution that dies away with attenuation constant alpha. So the second set of waves would be evanescent waves, the first set of waves would be propagating waves. So now what we can do then is use Maxwell's equations, which were shown early in the slideshow. We can use Maxwell's equations and take the appropriate derivatives to get the terms in the other components. So now we can get both the x and y component of E, and we can get the x and y component of H, remembering that we have assumed that we have transverse magnetic, so we have no H component in the z direction. So note that in this case, every field expression has a sine term, which means that unlike the parallel plate case, when we plug in 0, 0, every term will go to 0. So we can't have a TEM mode, because that would be, a TEM mode would be when we had a 0 and a 0. That would mean that all of the fields would go to 0. So in a rectangular waveguide, you do not have transverse electric magnetic fields. So that's the key difference between it and the parallel plate waveguide, which means that in a rectangular waveguide, you will always have a cutoff frequency. All right, so for the TM transverse magnetic MN modes, and also our mode has we have two mode numbers. So unlike the parallel plate where we had a single mode number, we have two mode numbers because we have to specify both A and B. So the boundary conditions restricted that big A is equal to m pi over little a, and that big B is equal to n pi over little b, remembering that little a and little b are the waveguide dimensions, so m and n are the mode numbers. And because gamma in the guide is related to a and b and also to h and omega squared and mu epsilon, then we can write gamma in this form. And why would we want to do that? So we made a substitution for h. The reason we want to do that is we want to find out in the guide where is propagation possible. So you can see clearly, of course, if you want propagation, gamma has to be imaginary. So that would mean that this term under the radical would have to be negative. So omega squared mu epsilon would have to be greater than this sum, m pi over a squared plus n pi over b squared. So if you want propagation, it has to be greater than that. It has to occur when omega is greater than some omega cutoff. And the omega cutoff can be found by solving for the case where these two are equal, which means the cutoff for a given mode with a given waveguide dimension, the cutoff frequency is given by the following equation. Now I do want to mention one thing. This gamma, once again, has a bar over it. This is referred to as the waveguide propagation. That is different from gamma without the bar, which would be the propagation constant in free space. All right. So you can also talk about a cutoff wavelength if you are working with wavelength instead of frequency, and that can be found by using the relationship between the wavelength, the frequency, and the phase velocity. So when you do that, I want to note that here we have switched from radians per second in this expression to hertz in this expression. Notice the pi has gone away, and notice the factor of 2 has shown up. So we've switched from radians per second to hertz, and note here we're talking in terms of F. So if you solve then for the cutoff wavelength, you can get that from the following expression. So it's 2ab over m squared b squared plus n squared a squared square root. So sometimes it's more convenient to talk about a cutoff wavelength. All right, so wave parameters. Beta is the propagation constant, so assuming we have a propagating wave in the guide, we can solve for beta, and then basically you find out that you can factor out the intrinsic beta. So let's talk about what is intrinsic beta. Intrinsic beta is the square root of omega squared mu epsilon, which is what the propagation constant would be in unbounded media. So we pull out the beta, and then we have this expression under the square root sign, which relates the given frequency to the cutoff frequency. We can find also, in terms of cutoff frequency and frequency of our wave, we can find the propagation velocity in the waveguide, and we can find the wavelength in the waveguide. Finally, we can solve for the waveguide impedance. We do that by looking at the definition of impedance. So the definition of impedance is the electric field over the magnetic field in general, thinking of it very simplistically. So in looking at a TM mode, we take the X component of the electric field and the Y component of the magnetic field and divide, or conversely, negative Y of the electric field, X of the magnetic field. Either one will work. When you plug in from Maxwell's solutions of Maxwell's equations, the electric and magnetic fields, you can get the following expression for the impedance. So it's basically the impedance of the material times this waveguide factor.